In one of the previous lectures, we looked at how we can implement the list abstract data type using arrays in C. In this lecture, we'll talk about how we can implement the stack abstract data type using arrays in C. And the logic to implement the stack using arrays is more or less pretty similar to how we implemented the list abstract data type. The storage structure is exactly the same, and operations as well that we are going to use to implement stack abstract data type are also pretty similar. In fact, the stack abstract data type can be defined in terms of the list abstract data type, and I think I will use that approach to also drive the point that one abstract data type can be defined in terms of the other abstract data types. So we can reuse the implementation of the list abstract data type that we have already done to implement a stack. So to recap, stack abstract data type, the model is nothing but a bag of elements, data items. So it's basically a set of data items or a bag of data items, or you can also call it a collection of data items. So one interface that we use to interact with this data model is a push operation, which basically pushes an element E into the stack. The element can be of any type. It can be an integer, a floating point number. It can be also a complex type like a struct in C. It can also be another abstract data type with its own model and operations. Now, push basically pushes the element E into the stack. The abstract data type doesn't define how this push is implemented. You can assume that E is available in the model, and E will come out at an appropriate point when we call another operation called pop, which pulls out elements from the stack. So push puts elements into the stack, and pop removes elements out of the stack. Stack as an ADT has a property called LIFO, which is called as last in first out, which means that the element that is popped out of the stack should be the most recently pushed element into the stack. So these two are the fundamental operations for the stack ADT. You can also define other helper functions like size, which will be useful to count the number of elements in the stack. So if you have, say, 6 elements in the stack, this will return 6. Another property of push is if it pushes an element into the stack, the count of the number of elements is incremented by 1. So size would return the earlier size plus 1. And pop would also change the elements in the stack. So the pop decrements the count by 1. So this increments the count by 1, or increments the size by 1, and then this decrements the size by 1. This is just an abstract type definition. It has nothing to do with implementation details, storage structures. Those details are something that we're going to talk about when we actually implement the stack using different data structures. In this particular case, we're going to do it using arrays, and we're going to reuse the implementation that we had for a list that we had done earlier. Another important operation that people generally define for a stack ADT is called peek, or they also call it a stop, which basically behaves as a pop, except that it doesn't modify the stack. It just tells you what is the element that will be deleted if pop were to be called on the stack next. To give an example, so generally represent stack as a stack of items, one on top of the other. So when you push element into the stack, the items are stacked up on top of each other. That's the reason why the data structure or the abstract data type is called a stack. So one is put first, and then you push 2, push 3, push 4. So this is the state of the stack. And then when you call pop on the stack, the element that is deleted is the element that's right on the top of the stack. So after pop is called, so let's represent the timeline from top to bottom. 4 is removed, and 3 is removed. And we call pop again, 2 is removed, and so on. So when you call a push again of say 10 is the one that's pushed, and then you put it in here. The stack operations are pretty intuitively supported by arrays in C. The plan is very simple. So what we have to do is whenever push is called, we are going to add the element to the array from the left. So if you take the indexes of array as 0, 1, 2, 3 and so on, you use the 0th index to push whatever element that is intended to be pushed, and whatever elements come through, like say you have a queue here, so the next thing that we do is to push q from the left. So always the 0th index is used to store the element that is pushed. Other elements that are present in the stack are shifted right by one index. So you can maintain a size variable which will be 0 initially, and whenever an element is pushed, size is incremented to keep track of the number of elements. So if you push E, the size would become 1. If you push Q, the size would become 2, and so on. Size would also be very useful to serve as a sentinel to tell us till what location you have elements in the stack. Pop operation also happens from the same index of 0. So if there's a pop, what you would do then is to basically, this is 0, 1, 2, just remove the 0th element, which means you would have to then left shift all the elements by one index. So you basically remove R, so R goes out as a result of your pop. This gives out R, and Q is left shifted by one index and E is left shifted by one index. So you have Q here and E here, and then the rest of the elements. Again, you might have E here, you just don't want to delete E, but we don't care about E because essentially we are maintaining a size here which will give us the limits or bounds of our stack inside the array. So if size is decremented for pop, it becomes 2, and obviously because it's 2, the end of our stack is the first element. So the plan is to basically implement a stack as a single-ended data structure by supporting operations of push and pop from the same side, from the same direction of the array, and using our index of 0 to store the latest element that is pushed. And obviously that will be the element that will be popped out because it's a LIFO data structure. So the last in element would be at 0 because we're using 0 as the position at which the pushed element is put in, and that is the element that has to be popped out as well. So as soon as a new element comes to be pushed to 0, the older element that is already present at 0 would be shifted by one index, and when you're popping out the element out of 0th index, you would left shift the next most recently input element, pushed element, to the 0th index, which will be popped out again if pop is called. So this way we can use an array to maintain the LIFO structure for a stack. And size is obviously a simple return of the value of the variable size that we maintain. isEmpty is another useful operation which is also very simple. You just see if the size is 0. Top is just returning the 0th element of the array. If size is 0, obviously top will be null because you don't have any elements in your array and top doesn't make sense. So let's try to see how we can implement push using the list operation. So all we do is, if you remember, we have a function of insert or an operation of insert in the list abstract data type, which would take the element, index, and the list. So all we would do to implement push is to call insert on the list. Obviously list will be backed. List is again an abstract data type which we had already implemented using an array, and we would reuse the same implementation for stack array implementation. So we would just call insert with the element, and as we had seen, we'll always insert at 0 the index and L. So every time push element is called, we would call insert element 0. And if we remember the implementation of insert does the same very thing that I was talking about. It basically puts the element that is to be inserted in the index and then right shifts all the elements that will present after the element to give space to the new element. And we also maintain a size variable to keep track of the number of elements, which would fall in place. Pop can be implemented using the remove or delete call that we had. So whenever pop is called, I would just delete the 0th element from the list. So if you remember, the operation of delete was to have the following arguments. You have the index from which you delete the element, and then you had the list. So push is implemented in terms of insert. Pop is implemented in terms of delete. So if you take a list, and you have elements in it, just representing the elements with a dot, and dash is to indicate there are no elements. So pop would just call delete, that would remove this element and send back as a written value. And as part of the implementation of delete, we saw that all the elements that are to the right of the element that is being deleted would be left shifted by one index till the size of the array, and the new size of the array would be the old size minus 1, and here the new size would be old size plus 1. And the operation of peek or top would just return get element at index 0, and this is done only if the size is greater than 0, otherwise we return a null. Size is also very simple, just returns the size. And isEmpty just returns size of L equals to 0. So if size of L equals to 0, it returns a true or a 1. If it is false, it returns a false or 0. This is the piece of code that I have written to implement stack abstract data type using array. So this particular data structure here represents the stack. So it's a struct and it contains two elements. Say it's a stack and it contains two elements. The first element is the array of a predefined size, and then the second element is the size, which is helpful for us to keep track of the active stack in the bigger array. And again, we are going to pass the pointer to the stack to all our functions. So we have defined push, pop, top, is empty, size. So these 5 operations are the stack abstract data type, but insert and delete is the same as the list operations. We are going to define push, pop, top in terms of insert, delete, and get operations. Get is nothing but get element at index. And then we have three helper functions to initialize the stack. We'll see the functions as we go through the code. Print is to just print on the stacks to see what are the elements in it. Get stack is to initialize our structure, assign the memory to the structure pointer, and return the pointer so we can pass it to arguments, pass it as arguments to functions. So this is the main method. Then let's first see insert. This is same as the insert function that we implemented for list. This is just to so this part of the code is to do the range check, and so this part of the code is to right shift the array that is to the right of the index at which the element is being inserted. So in the case of a stack, we always insert elements at 0. So this will make sure that all the elements that are present from 0 and so the entire array is right shifted till the size of the array. But then this right shifting is done starting from the end of the array, end of the stack structures, end of the elements of the stack. So to take an example, assume you have elements 5, 6, 10, 1, 5, 4, and then obviously so these are the indexes 1, 2, 3, 4, 5. You have size as 6 because there are 6 elements. So when you try to insert element 8 at index 0, all you do is you start from the rightmost element of the list and copy 4 here and copy 5 here and then copy 1 here and then copy 10 here and then copy 6 here, copy 5 here, and vacate this spot that can be occupied by the element that is being inserted. So this is how this is done, and delete again is analogous. It'll just do the reverse of insert. It removes the element. Obviously for insert you have to also update the size to old size plus 1. Delete would do everything in a reverse manner, so it just removes the element from whatever index is given as input. For stack we always do it at index 0, and all the elements that are remaining are left shifted and the direction is from here. So for push the right shifting happens from the end. For pop the left shifting happens from the left. Right shifting happens from the right, and left shifting happens from the left for pop. So let's quickly understand how this pop operation works. So this is where you insert the element and then increment the size and insert. Then you also do a range check for the index for delete and collect the value so you can return it from this call. Start from the initial index that you're trying to delete element from, and then start from it and do your left shift till the size of the array, and then you decrement the size and then return the value that you've saved. So you have an array with elements, 6 elements. So your size is 6. And so when you call pop, or sorry, when you call delete, talking about delete at 0 for the list, you start from the 0th element and you do your left shift. So first you basically save your element into a variable, say its value, so that you can return it later on after your shifting is done out the call. So this is saved, and then you left shift 2, and then you left shift 3, then you left shift 4. Basically this element is left shifted here, and then you left shift 5, and then you left shift 6 as well to end your shifting operation. Obviously, this 6 here remains as it is, but we don't care about it, because when you decrement the size, so size was till here before the call is made, but then when you decrement the size would be till here, and as far as you're concerned, your array starts from 0 and ends at this element. You're not worried about what is there after this. Even though the memory exists, the elements that might have been put into the array might exist, but logically you're not worried about that. Push just calls insert the element at 0 in the list. I've represented it as a stack in your definition here, and pop is implemented as delete from the index 0 from the stack. Size just returns the size. Top just returns the 0th element. One possible modification that we might have to do here to be safe is to add the condition that if the size of the stack is greater than 0, return, else we return an error value -1 or none. And isEmpty essentially talks about comparing the size of the substack to 0, then returning 1, otherwise it will return 0. That's it. We are done with the stack implementation using arrays. So this is the array that's used to store the elements of the stack. I mean, this is a very useful way of implementing a stack, which already uses the code that we defined for a list. And because you're reusing code, you're less likely to make errors. When you're reusing thoroughly tested code, you're less likely to make errors because you're writing less code. And this also exhibits the power of composing multiple abstract data types and building a different abstract data types. Stack implementation implements the Stack ADT. It uses the List ADT, and using List ADT, it would access the list implementation. Now, if you change the list implementation, it doesn't matter because it just depends on the method calls it makes are the ones that are defined in the List ADT. So you can just change this and you can use a different implementation. So this is an array implementation, and you can change it with a linked list implementation. It doesn't matter to Stack because all it is expecting is for these implementations to obey the contract provided by the list abstract data type. So this way your design is more decoupled and extensible. Alright, so that's it. It's a very simple implementation. So let's meet the next lecture to talk about the Stack implementation using linked list.